Hello. I know, I know. I probably what. I get what's like. Oh, yeah, like the rest of it goes. Yeah, no, Yeah, I don't see. Yeah. Back into me in that parking lot. Oh, going back on you. Yeah, there's an article. There's some stuff.
All right, folks, we'll go ahead and get started here. It's good to see you all. Now we've got our room. We're getting all comfortable with this. I think this actually seems to be a pretty good setup. You guys like it here, at least better than the other room. So, I'll go and open us up in prayer, give you a little bit of a heads up what we're going to cover today. So, dear Heavenly Father, thank you for the chance to be working with each of the students in this course, Lord. I pray that you would help them here in their time at APU as they're getting to learn a lot of skills that are going to serve them well in their future. Pray that you would help them to stay motivated, interested, and engaged with the things that they're covering, and also the things that we cover in this course. It'll be clear. Pray that you would help them in their spiritual formation as they get a chance to study scripture, to become familiar with the theological concepts we want to be guiding our lives by. Chances to be having a shared worship experience, a lot of just neat things that they're getting the chance to have. And so just we ask you to be with us in this time. In Jesus' name we pray. Amen. So now we've actually covered the material that I was hoping to cover for bags, at least in terms of the lecture. You know, I gave you an example of what that looks like. And so you have that as some information. So I'll just do a quick little review of that. And then start to move into some new material. So you guys have the sample code that I gave you. So it's a very bare bones implementation of a bag. It doesn't have an application, but it does have a driver program. So please definitely take advantage of that to help you get some tips and ideas of where you want to be going from there. But just using this one slide that I keep coming back to. So we have like 7 different abstract data types we're going to be viewing it as we go through the course. We've now, in terms of what we've covered in the lecture, we've covered bag. And so we talked about 2 different possible implementations. And anybody remember what those were? We covered in lecture. Yeah. Yes. So you either can have a linked or an array implementation. And the way that they did that with the nomenclature was you could have like array bag or linked bag as a way of just as a mnemonic. It's almost like using the names, you're using it to help document what you're trying to accomplish. So data access, this is where we start to be thinking about cybersecurity. And so what you have with the interface is this is what you're exposing to the user. Okay, that means that this is the only thing that they have access to, and that you're trying to leverage. So the interface is defining what those things are. So I've used a car analogy with a car, at least according to the driver, needs a steering wheel, a brake, a gas pedal, basic things like that. So those are the types of things that are exposed. You now are aware of 2 implementations for a bag, but there's going to be some other things that we're going to get into we haven't gone into yet. We can be thinking about, well, what about recursion or iteration? Those are 2 ways of doing searching. And also it can come up in sorting. And so those are some of the stuff that we're going to talk about. Well, for today, we're going to be, before we get into the next type of abstract data type stacks, we're going to be talking about performance. And we're going to start to be thinking about algorithms. When we start to look at performance, it's going to be mentioning a couple different ways that you can do an implementation. And so that's the other part in the course that we are going to continue to be thinking our way through. So I'm going to close out for the lecture notes for now, and then go over to a video. And then as we typically have been doing, I kind of give a little bit of narration about that as we go. And so let's go ahead and so we'll have basically for chapter 4 is what we're going to be reviewing as the efficiency of algorithms. So I think I got the video a little bit louder today. So hopefully that'll be a little bit better. So hopefully it doesn't boom too loud on the flip side.
This lecture introduces the terminology and methods that computer scientists use to measure the efficiency of an algorithm. Manufacturers are regularly introducing new computers that are faster and have larger memories than their recent predecessors. Yet you're always asked to write code that is efficient in its use of time and space, which is memory. Such efficiency may not seem as pressing an issue as it was 50 years ago when computers were much slower and their memory size was much smaller than they are now. Even so, efficiency remains an issue, in some circumstances a critical issue. For example, when a search is performed on the internet, millions or billions of records of information must be searched and analyzed quickly enough that it feels to the user that the response is immediate. What is an efficient algorithm? Well, algorithms have both time and space requirements. This is called the complexity of the algorithm. Measuring this complexity is called the analysis of algorithms. When we assess an algorithm's complexity, we're not measuring how involved or difficult it is. Instead, we measure an algorithm's time complexity, the time it takes to execute, or its space complexity, the memory it needs to execute.
So they already talked about this a little bit, but why would time be important? Like if you're searching like just 10 items, that's probably not an issue with how well that algorithm is performing. But if you're trying to scan for 1 million or something like that, that's going to make a lot bigger impact. And so that's what that is. Or you having a lot of computation that have to be done, that's going to be an issue. What about space? We've talked about that a little bit when we thought about the difference between an array implementation versus a linked implementation. What happens when you run out of room in an array? You have to double the size of the array. So we can see that's what we are dealing with versus a linked. Immediately, it takes more space per single element in that data set, but you don't have to think about doubling the array size and then having to move things over, and all that's going to take some time and effort. So these are the type of things that we're getting a chance to be figuring out, so we can make a decent argument for analysis of what if
the time and space complexity.
If algorithm approach 1 versus algorithm approach 2 is better or worse.
Of an algorithm usually have an inverse relationship. If you try to speed up an algorithm, you will often need more storage. If you try to reduce storage, you may increase the time requirement or slow down the algorithm. Our measure of complexity of an algorithm should be easy to compute, definitely easier than implementing the algorithm. We express this measure in terms of the size of the problem. This problem size is the number of items that an algorithm processes. For example, if you are searching a collection of data, the problem size is the number of items in the collection. Such a measure enables us to compare the relative cost of algorithms as a function of the size of the problem. Typically, we're interested in large problems. A small problem is likely to take little time, even if the algorithm is inefficient. We cannot compute the actual time requirement of an algorithm. After all, we haven't implemented the algorithm in Java, nor chosen a computer to run it on. Instead, we find a function of problem size that behaves like the algorithm's actual time requirement. Therefore, as the time requirement increases by some factor, the value of the function increases by the same factor and vice versa. The value of the function is said to be directly proportional to the time requirement. Such a function is called a growth rate function because it measures how an algorithm's time requirement grows as the problem size grows.
So if it's like 10 items, that would be one thing. 100, 1,000, 1,000,000. This is where we want to be analyzing. And so you're going to see these curves that'll be coming up later in chapter 4. And then we'll get a chance to see some of this in this video. That those are those large case are the ones that we really need to be aware of.
Because they measure time requirements, growth rate functions have positive values. By comparing the growth rate functions of two algorithms, you could see whether one algorithm is faster than the other for large-sized problems. Using growth rate functions for comparisons gives us a common basis for comparison that is independent of how the algorithm is coded, what computer it is run on, and the data type used by the algorithm. While each of these can impact the speed and storage requirements of the final implementation, They are separate issues that are dependent on the actual implementation. Since we can assume that each of our algorithms will be applied to the same data on the same computer, these do not need to factor into our comparisons. You may think that you're not likely to write a program in the near future whose execution time is noticeably long, and you may be right. But let's look at an example where execution time may be longer than expected. Consider the problem of computing the sum 1 plus 2 plus 3 plus 4 and so on up to n for any positive integer n. The first algorithm that may come to mind should be a simple loop that accumulates a sum from 1 up to the number n. Algorithm B performs an even simpler task. It adds 1 to the sum, then it adds 1 twice to the sum, then 1 is added 3 times, and this continues until 1 is added to the sum n times in the inner loop. Finally, algorithm C uses an algebraic identity to compute the sum. If you execute this code,
So if we were, you can almost think like this is a an algorithm race here. And so which one's going to be performing better? So here we have option A, option B, and option C. Anybody, maybe you've read ahead a little bit. Anybody have an idea which one you think would work better? Yeah. And why would you think that's true?
It's just gonna do the operation once.
Exactly.
It's less operations.
We're going to be talking about something called big O notation, and they'll describe it. But there's all kinds of operations that have to take place, and this is just one algebraic expression, and then you're done. So that's going to clearly be an example of an improvement. And so this is how you can be trying to do an argument for one algorithm or another. So do you want it to go fast? Do you want it to use minimal resources? This is actually going to be good in both of those criteria.
with n equal to 10,000, we get the right answer of 50,005,000 for each of the algorithms. Now change the value of n to 100,000 and execute the code again. Once more, we get the correct answer, which this time is 5,050,000. However, you should notice a delay in seeing the result for algorithm B. Now try 1 million for the value of n. Again, you'll get the correct answer, 500,500,000, but you'll have to wait even longer for the result from algorithm B. The wait might be long enough for you to suspect that something's broken. If not, you could try a larger value of n. The simple code for algorithm B takes a noticeably long time to execute, much longer than either of the other two algorithms. If it were the only algorithm you tried, what should you do? Use a faster computer? Well, that might be a solution. It's clear that we should use a different algorithm. So how can we tell which algorithm is the slowest and which is the fastest? The integer n is a measure of the problem size. As n increases, the sum involves more terms. To measure the effort or time requirement of an algorithm, we must find an appropriate growth rate function. To do so, we might begin by counting the number of basic operations required by the algorithm. An algorithm's basic operation is the most significant contributor to its total time requirement. These statements are highlighted in yellow in the algorithms.
So I think most of, if not everybody here has had discrete math. And so this was a concept that was introduced there. And so now you're getting a chance to pick it up in this course if you haven't seen it in other classes. And so we're going to circle back to try and figure out, well, what is a significant statement that would be the driver that we can come up with an order of magnitude type of answer of how good or bad this is going to perform.
For example, algorithms A and B have addition as their basic operation. Another algorithm that maybe sees whether or not an array contains a particular object has comparison as its basic operation. The most frequent operation is not necessarily the basic operation. For example, assignments are often the most frequent operation in an algorithm, but they are rarely basic. Loop control statements such as for or while loops are often not basic operations either. Ignore operations that are not basic, such as bookkeeping operations like the initialization of variables. The operations that control loops and so on will not affect our final conclusion about algorithm speed. For example, algorithm A requires n additions of I to the sum in the body of the loop. we can conclude that algorithm A requires time that increases linearly with n, even though we ignored operations that are not basic to the algorithm. Thus, A's growth rate function is n. Now let's count the number of basic operations required by algorithms B and C. The basic operation for B is addition. For algorithm C, the basic operations are addition, multiplication, and division. Remember, these counts do not include assignments and the operations that control the loops. If we plot the growth function for each algorithm, we see that algorithm C is flat.
So it kind of leaped over that fairly quickly, and we'll get a chance to have that in the textbook and in our lecture notes, but see if I can get it back to one full table here. So big O notation, this is n. They'll talk about that. Big O notation, the largest term is this n squared, so that would be n squared. And this is just a single digit, so this is just 1. So just as that assertion where we talked about previously, definitely this third algorithm C is going to be performing a lot better. And let's look at the graphs. I think it'll be pointed that out.
If we plot the growth function for each algorithm, we see that algorithm C is flat or constant. No matter how large n grows, algorithm C takes only 3 basic operations, so algorithm C is independent of n. Algorithm A grows gradually with n. This is linear growth, and we see that algorithm A requires time proportional to n. Algorithm B grows very quickly. With only 10 items to add together, it already requires more than 5 times the number of operations needed by algorithm A. Typical growth rate functions are algebraically simple. Since we're not likely to notice the effect of an inefficient algorithm when the problem is small, we should focus on large problems. Thus, if we care only about large values of n when comparing the algorithms, we can consider only the dominant term in each growth rate function. For example, for algorithm B, we can say the quantity n squared plus n divided by 2 behaves like n squared when n is large. First, n squared is much larger than n for large values of n. So n squared plus n divided by 2 behaves like n squared divided by 2. Also, n squared divided by 2 behaves like n squared when n is large. In other words, for very large n, the difference between the value of n squared plus n divided by 2 and that of n squared is relatively small and can be ignored. So instead of using the quantity n squared plus n divided by 2 as algorithm B's growth function, we can use n squared, the term with the largest exponent, and say that algorithm B requires time proportional to n squared. We conclude that algorithm C is the fastest and algorithm B is the slowest. This table shows how growth rate functions that you're likely to encounter can grow in magnitude as n increases. From this data, we can see that algorithm.
So when you identify what that big O notation driver is, you can see going in this direction where it's smaller is really where you want to be trying to go, where like we had that's just single, it's just a directly just 1 or and stuff like this. N squared, n cubed, 2 to the n, these are just you're not going to get, there's just non-starters. So you want to try and come up with this. And so this is where, when we start to get into the sorting and searching, some of these more elaborate algorithms, just if you have a large data set, it's going to be a lot better to use.
Whose growth rate functions are log n, or log base 2 of n, take much less time than algorithms whose growth rate function is n. Although the value of n log n is significantly larger than n, either of those functions describes a growth rate that is much slower than n squared. This table also shows that when analyzing the time efficiency of an algorithm, we should consider large problems. For small problems, such as for when n is less than 100, the difference between the execution times of 2 solutions to the same problem is usually insignificant, unless one of those solutions has a growth rate function of 2 to the n or n factorial. Algorithms with those growth rates should always be avoided. Here's a graph that shows the same information, it's easy to see visually how rapidly algorithms with a growth rate of 2 to the n can increase in time.
It doesn't even show the n factorial. That would have been even steeper than what they showed, just to keep that in mind.
Computer scientists use a notation representing algorithms' complexity. For example, consider the algorithms A, B, and C, and the number of basic operations that each requires is shown here. Instead of saying that algorithm A has a time requirement proportional to n, we see that A is of order at most n. We call this notation big O since it uses the capital letter O. We read O parentheses n parentheses as either big O of n or order of at most n. Similarly, since algorithm B has a time requirement proportional to n squared, we say that B is of order at most n squared. Algorithm C always requires 3 basic operations. Regardless of the problem size n, this algorithm requires the same time. We say that algorithm C is order of at most 1. Let's look at what happens if we double the number of items to process for each of the various growth rates. If the growth rate is 1, there's no effect. If the growth rate is log n, doubling the number of items results in a negligible effect, only 1 more unit of time. If the function is of order at most n, then the time required will double. From there, we can see that the time requirement begins to increase greatly when the number of items is doubled. Doubling the
We're going to see some examples where you're stuck, based on some limitation. Maybe you're forced to use an array. We're going to get into some things that you can help to make an array a little bit more efficient. So you may have one of these things that aren't as great, but based on your particular application, you're going to go for it anyway. So this kind of gives you the bad news in a nice way to see that.
The number of items, even for small problems, results in quadrupling the time requirement for problems of order at most 2 to the n. Now, supposing a computer can perform 1 million operations per second, how long will it take an algorithm to solve a problem whose size is 1 million? We cannot answer this question exactly without knowing the algorithm, but the computations here can give you a sense of how the algorithm's big O would affect our answer. An order of at most log n algorithm would take a fraction of a second, whereas an order of at most 2 to the n algorithm would take many trillions of years. Note that these computations estimate the time requirement of the growth rate function of various algorithms. Although this approximation is not universally valid for many algorithms, it is reasonable. We can use algorithms of big O of n squared, big O of n cubed, or even big O 2 to the n, as long as the problem size is small. For example, at the rate of 1 million operations per second, an algorithm of big O of n cubed algorithm would take 1 second to solve a problem whose size is 100. A big O of 2 to the n algorithm would take about 1 second to solve a problem whose size is only 20. To picture some of these growth rate functions, let's look at the number of operations for some simple loops. Here we have an algorithm A from earlier that adds I to some n times. If each watch represents an addition, we'll see a single addition each time through the loop. We perform the loop n times, so there'll be n additions, and we have an algorithm of order at most n. Here's another similar algorithm, but it is of order at most 1. We still have a loop, and we still have n, but why does this loop have a big O of only 1? The key is that the loop always executed the same number of times, no matter what the value of n. We always add n to some 1,000 times. If n is 1 million, we still only add n to some 1,000 times. If n is 3, we still add n or 3 to some 1,000 times.
So for the most case, for this course, you're not going to have to compute what the big O notation is. You're going to be given it. But this is trying to give you a little bit of a sense of how to determine that in the future. Say when you're developing your own algorithm, you want to get some assessment of which would be better for your application. This is how you go about doing it.
So even though the algorithm uses n, the time requirement for this algorithm is independent of n. Here we have an algorithm of big O n squared. When we are examining nested loops, we can examine the inner loop first. We see that we have a loop similar to the earlier one that iterates n times.
So you have a loop inside of a loop. So that's where you get in the n squared. you haven't sort of seen that.
So we can represent this as we did earlier. The operation performed by the inner loop is repeated n times, and so we can draw the same row of watches a total of n-1 times more. We end up with a grid that is n operations across and has n rows. This gives us n times n operations, or a big O, n squared for this algorithm. Here's another algorithm that has the same growth rate function. Here, the body of the inner loop requires a constant amount of execution time each time that it executes, and so it is order 1. If we again represent time at the watch, a row of I watches represents the time requirement for the inner loop. Here are the first 2 times it executes. Since the inner loop is the body of the outer loop, it executes n times. As we computed earlier, the sum 1 plus 2 plus 3 plus 4 and so on up to n is order at most n squared. So here we have nested loops, but where the outer loop is clearly dependent on n and the inner loop is dependent on I. But if we look closely at this algorithm, we see that the value of I varies from 1 to n. And so I is dependent on n, making both loops dependent on n.
So you can see in that last part of that video that the two ones were big O notation n squared. One of them was very much so. The other one was not quite as demanding, but it still ended up being classified as a big O notation of n squared. So I think just for completion, I'll go ahead and do the second video, and then I'll comment on some of the lecture notes and maybe put a little bit more context in for that. So let's go in and just watch this one. So that's pretty much set the stage, and this is going to continue that here. So this is going to set up what we're going to be seeing again and again. So we had 2 implementations of BAG. So now we're going to be looking at, well, what about the array implementation versus a linked implementation? And basically, we're going to find that some operations are more difficult for one versus the other. So it's an analogy is like you go buy a car and they says, well, it's going to get a miles per gallon of 30 or 40 miles per gallon. But really what it means, it depends on how you're going to use it. And so this is something like that. You really have to be looking at the details a little bit more, but this is going to be setting up. Some methods are going to be more challenging for one versus the other. So keep that in mind.
This lecture compares the ADT BAG implementations, array BAG, and linked BAG. When comparing implementations of an ADT, we want to consider significant differences in efficiency, such as the difference between big O of n versus big O of n squared, or between big O of 1 and big O of n. The specific number of operations is not as important as the concept of an algorithm being of order at most some function. We also need to consider the frequency of the various operations in the application that will use the ADT. Then, depending on the application, we may decide to choose a different implementation. For example, implementation A may have an add implementation that is significantly more efficient than implementation B's add implementation. But the contains method of implementation B is significantly more efficient than A's. We may decide to use implementation B if our application is going to be searching the ADT frequently, and we may decide to use implementation A if our application will add items to the collection but does not need to search or remove specific items very often. For some algorithms that operate on a data set, the execution time depends only on the size of the data set. For example, the time needed to find the smallest integer of an array of integers depends only on the number of integers, not on the integers themselves.
So we can have the best case, the worst case, or the average case. And so sometime one of those three are going to be the one that's most important that we want to be considering. So we're just introducing the best case.
Themselves. Finding the smallest of 100 integers takes the same amount of time regardless of the values of the integers. Other algorithms, however, have time requirements that depend not only on the size of the data set, but also on the data itself. For example, imagine that an array contains a certain value, and we want to know where in the array it occurs. Suppose our search algorithm examines each value in the array until it finds a desired one. If the algorithm finds this desired value in the first array element it examines, it makes only one comparison. In this best case, the algorithm takes the least amount of time. The algorithm can do no better than its best case time. If the best case time is still too slow, you need another algorithm. Now, suppose that the algorithm locates the desired value after comparing it to every value in the array. This would be the algorithm's worst case, since it requires the most time. If you can tolerate this worst case time, your algorithm is acceptable.
So let's say that there's a 1% of the time that you're gonna have a worst case scenario. So does that mean that you're gonna be driven by that or not? What if it's a 1 in 1,000, 1 in 1,000,000? It's still the worst case. And so those are some of the judgment calls that you're gonna have to make as you go forward.
For many algorithms, the worst and best cases rarely occur. Thus, we consider an algorithm's average case when it processes a typical data set. The average case time requirement of an algorithm is more useful but harder to estimate. Note that the average case time is not the average of the best case and worst case times. Some algorithms, however, do not have a best, worst, and average case. Their time requirements depend only on the number of data items given them, not on the values of that data. As we examine our two implementations, we can begin with the methods in our ADT bag that check the status of the collection. In both our array bag.
Okay, so this is where it's probably a little bit harder to look at them together, except for places like this. We had to implement all of the methods that were in the bag interface, right? But one of the things you'll start to pick up is then there were private methods. For example, for the linked implementation, you either can have a private method node or a private class node. That's something you don't need in the array. In the array, you need to do the resizing of the array. Those are some private methods that you needed. So those are the example of the things that you're starting to see that are a little bit different.
Bag implementation and our linked bag implementation, we can determine the current size of the bag and whether or not.
So in an array implementation, you have like this default capacity or this maximum capacity. Those are the things that we saw and are possible there. I did the streamline implementation that I shared with you. And so some of these complexities aren't there. You can keep that in mind. But both of them do keep track of the number of entries, but for different reasons. So.
It is empty or full by performing a comparison to the data member number of entries. Each of these methods only requires that a single comparison be performed no matter how many items are in the bag. Since these methods always take the same amount of time to execute, they are of order at most 1. As we examine the array bag add implementation, we see that each step in this method, detecting whether the bag is full, assigning a new entry to an array element, and incrementing the leg, is a big O of 1 operation. It follows then that this method is big O of 1. Intuitively, since the method adds a new entry right after the last entry in the array, we know the index of the array element that will contain the new entry. Thus, we can make this assignment independently of any other entries in the bag. Similarly, for the linked bag add method, all of the statements in this method represent big O of 1 operations.
So the characteristic of a bag, there's no order. So just you put something else in your grocery bag, you stick it in the bag. You can't say, well, that was the last one. It's not like it's in order. It probably when you stick it in the bag, if it's small, maybe it's going to go funnel down to the bottom of the bag. And so you're going to see those kind of characteristics. And so that's what we're getting a chance to get some insight here. Here we see in the linked implementation, we have this node. And so this is something that I mentioned that you need to have this private node class or method. And so that's something, but you don't need to have that in the array bag.
And so the method is big O of 1. The contains method searches the array bag implementation for a given entry. The basic operation for this method is comparison. As mentioned earlier, the method would make one comparison in the best case and n comparisons in the worst case, assuming that the bag contains.
So what do you think the big O notation would for that one would be, based on what he just said? Best case is 1, worst case is n. What do you think? Anybody have an idea? Well, the worst case is n, so guess what? It's big O notation n.
N entries. Typically, the method would take about n over 2 comparisons. We can conclude that the method contains is big O of 1 in the best case and big O of n in both the worst and average cases. To simplify our example, we've considered a fixed size array. Typically, an array-based bag resizes the array as needed. Doubling the size of the array is a big O of n operation. As mentioned in an earlier lecture, the next n additions then would share the cost of this doubling. Searching for an item that is the beginning of a chain of nodes is a big O of 1 operation. It takes the least time of any search of the chain, making this case the best case.
There was a nuance with the linked implementation that we discussed. So that talked about these cases. If it's, is it the first one? Is it the last one? Is it somewhere in the middle? And so it creates these 3 or more different cases. That's different than what's done with the array bag.
If the item is in the last node of the chain, searching for it is big O of n. This search takes the most time among the searches for an item that is in one of the nodes. And so this is the worst case. The actual time requirement to find an entry in a chain of nodes depends on which node contains it. And again, we can conclude that the method contains is big O of 1 in the best case and big O of n in the worst and average cases for the linked bag.
So far, we haven't seen an advantage or disadvantage for either going with an array or a linked implementation in terms of performance. But let's try a few more.
If we examine the code closely, we can get a feel for the relationship between the code and the efficiency of the methods. The basic operation of the contains method is the comparison that checks to see if the target item is in the bag. These comparisons are inside while loops. The while loop has 2 tests to determine when the iteration should terminate. The first is when the item is found. In the best case, this is the first item. And so we would have a big O of 1. The second test is when every item in the collection has been examined. This gives us our big O of n worst case. The ADT bag to array method implementations may appear similar to the contains method, but notice the loops end only once every item in the bag has been copied into the array that is returned to the client. This means that every item in the bag must be touched or copied every time this method executes. If our bag contains n items, the loop executes n times. So our to array method.
So this is a stressor. There's no way around it. You got to touch every element in your bag, either for an array implementation or a linked bag implementation.
Is big O of n. This is also true of the get frequency of method, since it also must touch or process every item in the bag when counting the frequency of the target item. We will see this as we examine the efficiency of other collections. If an algorithm must process or touch every entry in a collection, it will be big O of at least n. You may have noticed that the linked bag while loop test has 2 termination conditions. Both of these are in place so that the while loop correctly terminates after copying the last bag entry, even though only one test is actually necessary. Using big O notation, this table summarizes the time complexities of the operations of the ADT bag.
So this is the kind of tables that we'll be getting as we go into the later abstract data types. So we won't go through this lecture again, these video notes, but we'll have these summaries. And so you can get kind of stare at this a little bit. What is the difference? Do they seem pretty well balanced going from one to another? And so if this was the only issue, And some students have said this, one of the things I kind of do informal surveys to people like an array implementation or a linked implementation as you're going forward. And you can see here, there might be a little bit of an advantage going towards a linked implementation, that the clear has the potential of having it be a big O notation 1 or a big O notation of n. So maybe that's some good. And so just keep that in mind.
Back for the implementations that use a fixed size array and a chain of linked nodes. For some operations, multiple time requirements indicate the best, worst, and average cases. As you can see, all the operations have the same big O for both implementations, with the exception of the clear method. This phenomenon is unusual, but it reflects the simplicity of the ADT bag. Subsequent ADTs will have at least some of the operations whose time efficiencies differ according to their implementations. Let's look at the linked bag clear implementation a little closer. Here is the clear method that we presented earlier when implementing the linked bag class. This implementation is the same as the array bag implementation. It relies on methods that were previously implemented, and since it individually removes and processes each item in the bag, it is a big O n, similar to the array clear implementation. Here's an alternative clear implementation that cuts off the list by setting the first node to point to null. This marks all of the nodes in the bag and the items they hold for removal by garbage collection in Java. Since the bag has no entries.
So here we're seeing an example. If you can have this big O notation here, where so it's a big O notation of 1, this is going to clearly, at least for this, if you envision that you're going to have to be doing clearing of your data, say you have a bag and then you empty the bag, after you've gotten everything out of the bag is empty, so you're trying to mimic that behavior, perhaps a linked implementation would be useful for that. So this gets into why would you be using a bag, and that's where you get a chance to be thinking about that kind of a question with your project.
We also need to set the number of entries to 0. This alternative implementation has a big O of 1. When comparing several implementations of an ADT, if the problem size is always small, for example, where n is always less than 100, in most cases we can ignore the algorithm's efficiency. But as the number of entries in the collection grows, efficiency becomes critical. It is a good idea to test ADT implementations with large data sets to see how an algorithm's efficiency impacts real-world use. As we will see in other lectures, such as those on sorting, there is often a trade-off between an algorithm's efficiency and its memory requirements. Said another way, some algorithms that are very efficient with respect to time require a significant amount of extra storage to manipulate the data set. In other situations, algorithms require no storage additional to the data set may be very inefficient with respect to time.
Okay, so that gives us a nice introduction into efficiency of algorithms. And so it gives you the basis which we'll be using as we go forward from here to be comparing one to another. So let's see where we are here. So now we've covered all of the bags. We talked about the arrays, we talked about the implementation, we talked about the efficiency of algorithms. And so I'm just going to go page through some of these lecture notes here, because one thing that shows up in the lecture notes that doesn't show up in the video notes is piggy bank example. And this is one of the things I can go over on Thursday to give you an idea. And so we talked about a driver program, but we haven't talked about an application, at least in terms of what I've been showing you in Eclipse. And I don't remember exactly where it is, so I'm going to have to just page through this for a minute. Pretty sure it shows up in here. Well, since we're in this chapter, you have the video notes and you have the same kind of information here. And the charts, and so you can just be looking at this, how things change. And so this was comparison between an array and a linked implementation. And so they didn't have that nuance about to an array. I mean, so where's the clear? Didn't talk about that here, but this was an alternative to an implementation that they captured in the video notes. So that's something that you can be thinking about. Okay, well, anyway, there is one example that we'll cover on Thursday in a piggy bank example. And I think I've had a discussion with one or two of you about the application that you might be doing. And I think one or two of you might have done something that would be using something like that. And so there is an extra class that you need. So you're talking about coins. And so you have to devise a separate class that captures those coins. And so it's set up for US currency, but I could just as easily done it for Canadian currency, but the coins would be different. And so, and this is a smart piggy bank that we'll talk about, that it actually keeps a record of how much money is in it. You don't have to like take all the money out and count it to figure out what that is. Every time you deposit a coin, it knows what it is, and it keeps that as in its database of how much coinage is in there. It's an array implementation, and so you'll see that, and there'll be some of the things that weren't stripped out for the ones that I shared with you. And so we'll get a chance to be thinking a little bit about that. So this is the first of the different abstract data types that we're going to talk about. And so next, we're going to be talking about stacks. And so stacks is like a stack of books. And the first week when we were meeting in a mini library there, you could see all of the books that were stacked in a shelf. And you actually saw a little bit examples, if you looked at that bookshelf carefully, some of these books that are stacked this way versus some that are stacked in a normal way side by side. And when you have it side by side, you can get to a book immediately. You don't have to take the other books off. And so that's not the characteristic that we're trying to show with a stack of books. It's like this. And so my wife and I at our home, we have too many books. But it's kind of something that typically happens with people that are professors. But anyway, there's times when we have it stacked like this just to save a little bit of space. And so guess what? If I want to get to that bottom book, maybe I get lucky if I pulled it out real fast, but more than likely, it's just all those books are going to come down. And so we're going to start to talk about the characteristics of a stack that is different than a bag. A bag, you have no relationship to one element to another. That's not true with stacks. With stacks, you now have some of that information that gives those characteristics. So we walk through in a lot of detail of how a bag works, but as we get into these next ADTs, we talk about that less because we've already covered a lot of that material. And so this is what we'll get a chance to be seeing here. So we'll first get an idea of what are the characteristics of an ADT, and eventually we'll turn that into those methods that we need to implement. And so we'll then think about using a stack to process algebraic expressions. And so this is something that we're going to be revisiting several times. POSIX, there's different type of ways of you can be doing ordering of an expression. Has anybody ever had a reverse Polish notation calculator? I don't know if it's so popular now. People are still just using your cell phone, but it got into the different way that you were putting in numbers. And so if I was to do, I wanted to multiply 2 times 4, I'm actually expressing that one way, but for reverse Polish notation, it would be 2 times. And so you put the operator in a different order than what we're used to in a normal way that we communicate a algebraic expression. This is, we'll also talk about the program stack. This is one of those ways that something that's fairly familiar, especially since the majority of you guys are computer science folks, that's something that we want to be aware of. So I'll just do like, say, one or so video just to introduce this concept. And I'll just be mindful of time. I don't want to go over, but so this will be the first and the next set of videos. I divided these up into sections. And so this is where we get into stacks. So let's just introduce what is it, the general nature of a stack with this video.
This video describes the ADT stack and provides several examples of its use. In everyday life, a stack is a familiar thing. You might see a stack of books on your desk, a stack of dishes in the cafeteria, a stack of towels in the linen.
So maybe a characteristic that maybe you've heard of FIFO, for example, first in, first out. We'll get to that. But this a stack is LIFO, last in, first out. And so basically, and so a programming stack is like it always, the last item is the one that's on top. That's actually a characteristic that can be useful in certain things. And so when you start to program with stack, you want to take advantage of that. How would you be programming a stack versus what you did with a bag when you're going to start to use the advantage, the characteristics of the capability it has versus others?
Closet or a stack of boxes in the attic. When you add an item to a stack, you place it on top of the stack. When you remove an item, you take the topmost one. This topmost item is the last one that was added to the stack. So when you remove an item, you remove the item added most recently. That is, the last item added to the stack is the first one removed. In spite of our examples of a stack, everyday life does not usually follow last in, first out, or LIFO behavior. Although the employee hired most recently is often the first one fired during a layoff, we live in a first come, first served society. In the computer science.
Okay, first come, first serve. What does that sound like? My wife just had to go to the DMV, and guess what she had to do to get her new license? A queue. Yeah, a line or a queue. And that's what we're going to talk about next. And so that's what he's referring to.
In this world, however, last in, first out is exactly the behavior required by many important algorithms. These algorithms often use the abstract data type stack, which is an ADT that exhibits a last in, first out behavior. So
many algorithms use a LIFO. That's kind of a ding, ding, ding. Eventually, when you're doing programming, we have some canned things we're doing in this course. But if you wanted to do a LIFO type of action, here you have a data type, an abstract data type that's going to help you.
Here, for example, a compiler uses a stack to interpret the meaning of an algebraic expression, and a runtime environment uses a stack when executing a recursive method. The ADT stack organizes its entries according to the order in which they were added. All additions are to the one end of the stack called the top. The top entry, that is the entry at the top, is thus the newest item among the items currently in the stack. The stack restricts access to its entries. A client can look at or remove only the top entry. The only way to look at an entry that is not at the top of the stack is to repeatedly remove items from the stack until the desired item reaches the top. If you were to remove all of the stack's entries one by one, you would get them in reverse chronological order, beginning with the most recent and ending with the first item added to the stack. Let's look at the specifications of the ADT stack. A stack is a collection of objects in reverse chronological order and having the same data type.
So this is a top level description of what it is, and also specifying a requirement per se with the type of behavior that you're trying to show.
The method push adds new items at the top of the stack. Push has one parameter.
So it goes a little faster. It talks about it. You remember, this is the UML notation we talked about. They didn't use a CRC card, which was that they did at the very beginning. And so all of these different things have meaning, like this little plus sign, that means that it's a public. If that was a minus, that would mean that it's private. Those are just some of the distinctives in terms of the UML notation. Remember, T, we're using abstract, we're using a generic data type. So we're seeing that show up here. And so we're actually going to push, we're going to put on the stack a new entry. And so that's nothing's coming back. We're just putting it on, and that's what it means.
Entry we're adding to the stack. After each call to push, the stack should have one additional item. The method pop removes the item that's currently on top of the stack and returns it to the user. After calling pop, the stack has one less item than it did before the call. The method peek retrieves the item most recently added to the stack. This differs from the method pop in that the item is not removed but remains on the stack.
So once again, the generic data type, but in both cases, the pop and the peek, you get a chance to see what's on the stack, but when you pop it, it takes it off as well. So that's what they're trying to show, that distinction.
The stack is unchanged by a peek. Is empty checks to see if the stack is empty and returns true if it is. The method clear removes all items from the stack without returning them to the client. From these specifications in the UML, we can develop a Java interface, stack interface, using the generic type key to represent the type of data.
So this was a thing that I mentioned. The actual bag interface had more methods. Well, guess what? With a stack, there's not nearly as many methods. So it's going to be a little bit easier for you to get your arms around in terms of an implementation. This is all that you've got to do. So keep that in mind. And also having this descriptive text, the way that I've given those to you, and also the available to you with the Java resources the publisher makes available. I also put that on Canvas. You can catch that.
Data stored in the stack. To save some space, I'm going to remove the comments from our interface listing. Here's a short code snippet that creates an empty stack to hold string objects. It adds several items to the stack and then retrieves and removes 2 of them. We begin by creating an instance of a stack implementation to hold our collection of strings. 5 names are pushed onto the stack. The first name pushed onto the stack is at the bottom.
So we didn't talk about the implementation here. It just shows you the driver or application. And so, but we still have this common instantiation of what you do in your driver or application program, and then we start to see what the results are. So keep that in mind.
If our client would like to access Jim, each of the names above him would need to be removed or popped from the stack before Jim could be accessed. The string at the top of the stack is Joe. The peek retrieves it. So our print statement displays the message Joe is at the top of the stack. By calling pop, we retrieve Joe and remove him from the stack. A subsequent call to peek retrieves Jane. The pop retrieves Jane and removes it. 3 more calls to pop would remove Jill, Jess, and Jim, leaving the stack empty. After that, a subsequent call to either pop or peek would return null. Although programmers use parentheses when writing arithmetic expressions in Java, mathematicians use parentheses, square brackets, and braces for the same purpose. These delimiters must be paired correctly. For example, an open parentheses must correspond to a closed parentheses. In addition, pairs of delimiters must not intersect. Thus,
So how many of you have taken a class where you talked about compilers? Is that something you bumped into? This is another example where that's going to start to come in. Maybe you've done it with Java and it tells you have an imbalance of parentheses, or you have a syntax error. And so that's a nice thing about something like Eclipse. It's helping you to make sure that you don't have those type of errors. This is another place where a stack ADT can be useful for developing a compiler.
expression can contain a sequence of delimiters, such as this example, but not this. For convenience, we will say that a balanced expression contains delimiters that are paired correctly or are balanced. We want an algorithm that detects whether an infix expression is balanced. Let's look at whether this expression is balanced. We scan the expression from left to right, looking for delimiters and ignoring any characters that are not delimiters. When we encounter an open delimiter, we must save it. When we find a closed delimiter, we must see whether it corresponds to the most recently encountered open delimiter. If it does, we discard the open delimiter and continue scanning the expression. If we are able to scan the entire expression without a mismatch, the delimiters in the expression are balanced. The ADT that enables us to store objects and then retrieve or remove the most recent one is a stack. As we scan the expression, each time we find an open delimiter, we push it onto the stack. Each time we
So this is a generic stack, but it's giving the same kind of characteristics that you would find in a computer stack.
find a closing delimiter, we peek at the top of the stack. If the delimiters match, we pop the top delimiter off the stack. If the delimiters do not match, then the expression is not balanced. In this case, we've reached the end of the expression and the stack is empty, so the expression is balanced. Let's examine an expression that is not balanced and see how our algorithm performs. We begin scanning as in our previous example, pushing each open delimiter onto the stack. When we find a closing delimiter, we peek at the top of the stack. It does not match the stack top, so we can stop here. The expression is not balanced. This algorithm also identifies expressions that are not balanced because they have extra or unmatched open parentheses. In those expressions, the stack would not be empty after scanning the string. The extra open delimiters would remain on the stack. Let's put together a short implementation of our balance checker algorithm using a stack. First, we can write a short helper method that can validate whether or not delimiters are matching. This short method is paired, compares its two parameters, expecting the first to be an open delimiter and the second to be a closing delimiter. It then returns the result of ORing together several pair tests. If one of these tests are true, then the delimiters match. The method to implement our algorithm is the check balance method. The expression we're going to check is passed as the parameter expression. We begin by creating our stack, open delimiter stack, and initializing several important variables. Among these are isBalanced, which we use to hold the state of the expression. We can initialize it to true because at this point, no delimiters have been processed, so the expression is balanced. Then we implement our algorithm inside the check balance method. We scan the expression as long as it is balanced, and there are additional unscanned characters. With each character, we use a switch statement to check if it is an open delimiter. If so, we push it onto our stack. If it is a closed delimiter and the stack is empty, the expression is not balanced since there should have been a matching open delimiter on the stack. Otherwise, we pop off the top delimiter from the stack and call the isPaired method to help to see if it matches the current delimiter from the expression. We set isBalanced to the Boolean that is returned from this test. If the test fails, isBalanced is false, and we end the while loop scheme. If the character is not a delimiter, we do the default switch, which is nothing. After the switch, we increment index so that we can examine the next character and repeat the loop. Once the expression has been scanned, if there are still delimiters in the stack, the expression is not balanced. If the stack is empty, then either it is balanced because we scanned the entire expression, or it was found unbalanced since the closed delimiter was found when the stack was empty. Once the expression has been scanned, if there are still delimiters in the stack, the expression is not balanced. If the stack is empty, then either it is balanced because we scanned the entire expression, or it was found unbalanced since a closed delimiter was found when the stack was empty. In either case, isBalanced has already been correctly set, so we can just return isBalanced in the method.
Okay, so that introduces briefly the second abstract data type that we're covering in this course. And so a little bit on Thursday, but definitely next Tuesday, we'll get a chance to continue that conversation. So some things that were coming up next that you want to be thinking about. We're going to be getting your first project submittal. And so some of you have already started to talk to me about that. So if anybody else would like to, I can be around here for a few minutes or just send me an email. We can dialogue about that. And so that is the first time you're going to actually submit your code. And one of the questions include, does it work? Does it not work? And so if it doesn't work, you can submit, you can resubmit, you can do these things more than once, but giving you that insight into where you're at in your development. Also, I'm expecting you to share your code. Another thing I'm going to be looking for is, and this has come up in the past, is you want to make sure that you implement the interface. Okay, you just don't directly use something that's embedded in Java to bypass that. So you need to make sure that you include that bag interface.java. And then you could have another file that does array bag implements bag interface. That's what you want. And then your third program is going to be your application. So that's going to be the things that you're calling up the methods to serve the purpose of what you're trying to do with your application. Okay. Any other comments or questions that people have? All right, well, I'll end the lecture here, but I'll be around for a little while if anybody has anything they wanted to chat with me one-on-one. Thank you very much.
I got very good feeling.
Give me just 1 second.